All right, another calculus lesson. I know this is so exciting. So today we're going to talk about one-sided limits and continuity. We have a definition that's going to be important to us for sure next year, and this is called the definition of continuity at a point. This is something that you'll memorize. So a function is said to be continuous at a point provided that. So we have to have three things that are true. The first thing is the function has to be defined at that point. The second thing is the limit has to exist at that point. And the third thing is those two things have to be the same. Okay, so we're going to practice that definition of continuity on the next slide. As just a quick example, if we have this graph, this is A. This is like L. So in this case, we'll just make that something else. So in this case, this is f of c. Well, we'll call this, instead of A, we'll call it C. This is f of c. F of c is defined, check. The limit as we go to c from the left and the right is defined, check. But those two values don't equal each other. This f of c, which is this point, is not the same value. We'll call this, I don't know, we'll just make up a letter h. So that value, h, is not the same thing as the other value, l. Those are y values. So this would be a place where we could prove that we're not continuous at c. That's a situation where the first two steps are true, but the third step is not. Okay, so for the first example on this page, we're just doing one-sided limits, just getting comfortable with one-sided limits. So let's think about what this means. If I have a number line right here and 2 is on my number line, then if I want to be less than 2, it's this 2x minus 1, right? That's the part of the piecewise function that's less than 2. If I'm at 2, I'm at 1. And if I'm bigger than 2, I'm at x minus 2. Sometimes I think it helps if we just put this information like, on a number line so that we can get a better feel for what in the world is this talking about. So as I am approaching 2 from the left, this is from the left, basically what I'm doing as x approaches 2 from the left, I'm utilizing that 2x minus 1 part of the piecewise function. That's what I'm doing. The reason being is because that part is the part that's on the left of 2. Okay, so that's why I'm using that part, because we're approaching from the left, so we use that piece of the piecewise function. So that's going to be 2 times 2 minus 1. So what is that? 4 minus 1, or 3. So the limit as x goes to 2 from the left is 3. All right, let's look at the other scenario where we're coming from the right. So coming from the right, I need to utilize this portion of the function, the x minus 2 portion, because that's the portion that's on the right. So I'm going to rewrite this as the limit as x goes to 2 from the right of x minus 2. And I substitute in, 2 minus 2, and that is 0. So the limit as x goes to 2 from the right is 0. So the last part is asking, this is called the full limit as x goes to 2. This is, let's just write ourselves a little note. I call this the full limit. It's not just one side or the other, it's the whole thing. And do we approach the same y value as we're coming from the left and from the right? We don't, do we? Right? Coming from the left, we're approaching a 3. Coming from the right, we're approaching a 0. So that means that this full limit does not exist. And we're going to say because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. That's why that full limit does not exist. So that's some work on one-sided limits. How are we doing on that? Just one-sided limits. Is everybody okay? All right. So actually what I would, this first problem, I need to change. We're going to change this. We're not going to use definition of continuity with this first problem. I'm going to make it more like the ones in your textbook. This I got out of your textbook, and we're just going to determine the numbers at which the rational function is continuous by using limits. So if you would adjust those instructions for me, please. This is what some of your homework problems would look like by using limits. Okay, so this particular problem is has to really pull on our knowledge of rational functions that we worked on a little while ago. And so the first thing when we get a problem like this, the first thing we need to figure out is which numbers do we need to be working with. We want to know where we're continuous. In order to do that, we really need to know where we're not continuous. Okay, we're continuous in a bunch of different places. That would take a really long time to figure out. Instead, we need to focus on where we're not continuous. So what we would do with this rational function is we're going to factor it and see what's going on, what's really going on with this rational function. So we're going to pull from our memory on rational functions from a while ago. So the back sign is positive. That means the signs are the same. Something to multiply to get 8 and add to get 6. So it looks like a 2 and a 4. So I hope we can see that, that's going to go away. And when that goes away, do we remember what that means? When I cancel a factor from the numerator and the denominator, what does that mean in the graph? There's a hole. There's a hole there. So we need to make a note of that. There's a hole at x equals 2. And the piece that's left, the x minus 4 on the bottom, we know it can't be 0 on the bottom, right? So what does that mean? What's at 4? Do we remember? If it's 0 on the bottom, and well, so this basically is 1 over x minus 4. That's the reduction. When I simplify that equation, I get 1 over x minus 4. And when I put a 4 in the bottom, I get 1 over 0. What does that mean? We talked about it last time as far as limits go. What does it mean when you get the answer of a number over 0? You have a vertical asymptote, right? There's a vertical asymptote. So we have a vertical asymptote at x equals 4. So those are the two places where this function is not continuous. And that's what we need to focus on when we're doing our limits. All right, so let's do the limit for, I'm just showing you. So when that happens, and your homework is going to like step you through it, the limit portion, piece by piece. For the whole, what we're going to do is we're going to take the limit as x goes to 2, because that's the whole, of the whole x minus 2 over x minus 2 times x minus 4. Okay, this goes away like we showed. So that gives me the limit as x goes to 2 of 1 over x minus 4. Okay, so this is working with our knowledge from limits from last time. So we substitute the 2 in, right? We're taking the limit, we put the 2 in. So we have, that's 1 over 2 minus 4, which is what, negative 1/2? So that means, and they'll walk you through this wording on your homework, but that means since r is not defined at 2, the graph will have a hole. So we'll just say we'll just cut it down. So hole at 2 negative 1/2. Okay. So now let's work on the vertical asymptote. So this is how we're going to, this is what you would do. If it's a hole, that's the process that you're going to use. I'm just going to highlight. So this is what you would do if it's a hole. You go through this. You take the limit as it approaches the x value of the hole. You find the y value of the hole. You say there's a hole at 2, -1/2, or whatever. You're done. The vertical asymptote part. Okay, so when there's a vertical asymptote, we need to do the limit as x goes to 4. That's the value of the vertical asymptote of, and I'm just going to, if it's okay with you, I'm going to go ahead and go to the reduced form instead of writing the original form over again. If that's all right, I'm just going to the reduced form. We're still working with the same function. I'm just going to the reduced form. So when we take the limit, we get 1/0. And if you recall from our work from yesterday, this is the type 3, right? This is a type 3 where we get 1/0, which means there's a vertical asymptote. So we need to look at what's happening from both sides. So I'm going to go over here to 4. That's where I have an asymptote. Remember we did the 1/10 rule, remember that? So as I come from the right, I need to look at x being 4.1. So I do 1/4.1 minus 4, and that gives me, what does that give me? 4.1 minus 4 gives me a positive number. Coming from the left, I'm going to look at x being a 3.9. So 1/3.9 minus 4, that gives me a negative number. So what's happening, this is coming up and this is going down. That's what's happening at the vertical asymptote. I'm going to pause here for a second. So this is what we were doing last time. This is a type 3, which we don't have that many type 3s. This is not as common as type 2, where it was that indeterminate form. So let's kind of think about what's going on here. So we investigate the one-sided limits, and we determine that on the right side we're going up to infinity. This is going to infinity. On the left side we're going down to negative infinity. So therefore this is a D and E because the limit as x goes to 4 from the left of R, and I'm just being lazy and not writing the function in, and that's okay, you can do that. That tends to negative infinity, and that is not the same as the limit as x goes to 4 from the right of R, which tends to infinity. Therefore, there's a vertical asymptote at x equals 4. So what we're looking for here for our vertical asymptote is all of this business. Okay, so we're looking for this limit. We're looking for this part right here, which way we're going, and we're looking for that. Okay, we need to say which way each part goes. We go to negative infinity, positive infinity. That's what we're looking for. This is work. This is work to justify answer. And then where is this continuous? We would say it's continuous all real numbers except at x equals 2 and x equals 4. Okay. How are we doing? The very last problem, we're going to practice using definition of continuity. So what have we done so far? We practiced one-sided limits. We practiced this whole business of continuity, continuous at a point, using whether it's a hole or a vertical asymptote. And lastly, we're going to practice definition of continuity. In the definition of continuity, we have to do all these three parts. This number 1, number 2, number 3. We're going to do all three parts on definition of continuity. Okay? So, and it tells us, we're being told to use definition of continuity. Okay, we're going to use the definition of continuity. All right, so that's how this works. So let's look and see what happens. So first of all, we want to see where the function is continuous. It's the same kind of question as the previous one. Same kind of question, but we're going to use the definition of continuity to determine this. So where are we in trouble? Where is it possible for us not to be continuous? Well, parabolas are always continuous and lines are always continuous. It's not going to happen with the function itself. It's going to happen when we split. So what do we need to be concerned with? We need to be concerned with 0, the split. We have a split at 0, and we need to be concerned with the split at 2. So what are we going to do? We're going to have to do the one-sided limits at 0 and the one-sided limits at 2 to determine whether the limit exists or not. Okay, that's what we need to do. So let's start with, we're going to do x equals 0 first. We're going to focus on that one first. All right, so we're going to do the limit as x goes to 0 from the left. And I'm coming from the left, I need to use the x squared. If you need to draw out like this, like we did before with the 0, coming from the left is x squared, coming from the right is x plus 1, and the 2 coming from the left is x plus 1, right is at this. You can certainly do that. If that helps you to write that out so you have a better visual picture of what's going on, you certainly can do that. All right, so as I'm coming from the left of 0, I have to use that top branch, which is x squared. I plug the 0 in and I get 0. As I'm coming from the right from 0, I need to use the second branch, which is x plus 1. I plug in a 0 there and I get a 1. All right, so let's go through our steps for step 1 for definition of continuity. I need to see I need to know what f of 0 is. F of 0 comes from the branch that's equal to 0. Which branch is equal to 0, the top branch or the middle branch? The top branch, right? The top branch is equal to 0, so I plug in a 0 and I get 0. F of 0 is 0. Step 2, a definition of continuity. So I'll just make this smaller so you can see what I'm doing. So I just did step 1, f of c is 0. Step 2, does the limit exist? So step 2, what we're going to say, because these are not the same, the limit as x approaches 0 of f of x does not exist. And that's because the limit as x approaches 0 from the left of f does not equal the limit as x approaches 0 from the right of f. Step 3. Does f of 0 equal the limit as x approaches 0 of f? It does not. Right? 0 does not equal d and e. Therefore, not continuous at x equals 0. Okay, how are we doing? You're like, Dr. Wright, you're going so fast. Let me slow down for a moment. So I just did definition of continuity. The function value is 0. The limit doesn't exist. Therefore, the function value doesn't equal the limit value, so we're not continuous. Now let's check out at x equals 2. Okay, x equals 2. So I've got the limit as x goes to 2 from the left. From the left, I use the x plus 1 business. Plug a 2 in there. 2 plus 1 is 3. Okay? Then I do the limit as x goes to 2 from the right of f of x. From the right, I use the 5 minus x business. Plug in a 2 and I get 3. Oh. Okay. Step 1. We need to know what is f of 2. F of 2 is this bottom line, right? This is f of 2 right here. That's where 2 equals. So I plug a 2 in there and I get a 3. Number 2. The limit as x goes to 2 of f of x equals, since these one-sided limits are the same, then the full limit is 3. Oh, look at there. This one is working out much nicer for us. Step 3. F of 2 does equal the limit as x goes to 2 of f of x. That is true. Therefore, this is continuous at x equals 2. And the last thing, what numbers is the piecewise function continuous? We would say continuous all real numbers except at, come back over here, little thing, except at x equals, what was it, 0. All right.